can arrive. The big road then. Yes. Okay, I think we should start our session. Please take your seats. This first session of today is dedicated to EUSO and ASIM. Now, the first talk will be given by Etienne Parisot, and it will be about EUSO. You should have a...
Yes, and oh, it works. All right. Okay, so I guess I have to look here. Nice. Well, there are not so many people, so thanks for coming. I don't know what's the background of most people here, but maybe I will say things which are a bit too trivial. So I don't know. Anyway, so I'm going to talk about EUSO, which means, well, EUSO means Extreme Universe Space Observatory. And so we are looking for ultra-high energy cosmic rays, but also neutrinos. And since we are observing actually the Earth's atmosphere to do astrophysics, which is unusual, we're also seeing transient events in the atmosphere. So I have a preliminary word to say about the ongoing astronomical revolution. Not everybody is aware of that, but we are living a true revolution in astronomy. Since the dawn of time, we've done astronomy by looking at the sky, looking with our own eyes. then maybe with some telescope, but always visible photons. And the first revolution came in 19th century when we started to do spectroscopy. When you have access to spectrum, then you can see lines. You can see lines at different wavelengths, and you can start to do physics. You can measure chemical composition, temperature, velocities, and so on. You can start to understand what happens in the sky. So you can do physics, and that's the birth of astrophysics. Then the second revolution came in 20th century when we started to do multi-wavelength astronomy. So we extended the spectrum of electromagnetic waves, where we can see the cosmos to the entire spectrum, let's say from radio waves to gamma rays. And this brought the non-thermal astronomy, as we call it, so astronomy that is not just from radiating sources which radiate because they are hot, but a lot of physical non-thermal processes are involved, and this is the big field of high-energy astrophysics. And it's always fascinating to remember that everything we know about the cosmos, which is a lot, actually, we know the value of magnetic fields everywhere in many different places. We know the mass of stars, we know the temperature of stars, we know all these things. We've never been there, of course. We just look and we understand things. Because of this spectral dimension, the energy of the photons, which are different, and we recognize features, and since the physics is the same here and there, we understand things. So that's quite fascinating. But now we are living a third revolution, which will really be the third revolution, the 21st century revolution. And this is the revolution of multi-messenger astronomy. And the idea is that photons are not the only thing that come from the cosmos and bring messages. There are actually four pillars, four different messengers, the photons, of course, over the entire spectrum, but also cosmic rays, neutrinos, and gravitational waves. And in the very recent years, this new astronomy, we've heard about gravitational waves yesterday, and also now we are doing neutrino astronomy. And this gives us access to complementary informations about high energy astrophysical sources mainly. And so this is very important, and I'm going to talk of one of these pillars, which are the cosmic rays. So what are cosmic rays? Of course, cosmic rays are very well known from the space community. I don't have to explain what they are. We all know they are energetic nuclei traveling around in the galaxy. So they are mostly known from the space community through the irradiation that they do. As we all know, there are solar particles, which can be created in solar flares or coronal mass ejections and things like this. But there are also, of course, galactic cosmic rays traveling around the entire galaxies, and maybe a bit less known, there are also extragalactic cosmic rays reaching us. So the Earth is actually getting heavier by the minute from extragalactic matter. That's quite impressive. Very few, but still. Anyway, so so when these particles encounter an astronaut, that's not good for the astronaut, nor for the particles, by the way, they die. Sometimes they encounter electronic device, and we know that's bad too. That's why we need radiation hardness when we go to space to do experiments. And sometimes they miss the astronaut and the electronic chip, and they reach directly the Earth's atmosphere, and there they interact and produce secondary particles, and these secondary particles reach the ground, providing also some irradiation on ground, and that's how they were discovered. So people realized in the early 20th century that there is some residual irradiation on ground, which was unexplained. People realized that in deep mines, it's still, there is some radiation, so they understood that it's due to essentially natural radioactivity in the rocks. But so that led people to try to go away from the rocks to see less radiation. So some were working at the top of the Eiffel Tower, others went in the middle of lakes or seas. And but strangely, the irradiation did not decrease as expected if it really came from the rocks. So there is some elements of coming from the rocks, but not only. So people started to go up in a balloon, and Victor S. discovered the cosmic rays by, you have here the level of irradiation as a function of altitude clearly. So when you start to go up, it decreases a bit because you're further away from the rocks, but then at some point it starts to increase, and actually this radiation comes from the sky. So anyway, what are these particles? Is it light or matter? It took a lot of time to understand that they are actually charged. People were working with Geiger counters, and then in cloud chamber, so the tracks were deflected. So that means they were charged, deflected by magnetic fields, of course. Still, what people saw at that time were not the cosmic rays, were the secondary particles of the cosmic rays. And then the latitude effect that we all know, that you have more cosmic rays near the poles than in the equator, shows that even the primary particles are charged. And then Bruno Rossi has this nice idea to check for the west-east asymmetry and discover that these particles are positively charged. And that's about all you can do and say from the ground, because you don't see the cosmic rays, you see the secondary particles, and this will be important in a minute. So, so what to do? Well, you can study the secondary particles on the ground, and that was actually the beginning of a brand new field, which is simply particle physics. We discovered, just because these cosmic rays are very energetic, we had access through the cosmic rays to a new physics. So really, the particle physics was born from the sky, it was born from the cosmic rays. So people discovered antimatter, the muon, and all these things. I go quick. You have here all the particles, and I mention here, so the discoveries from the cosmic ray tracks. I mention here the strange particles because there will be a talk after by Zbigniew Plebaniak about strange quark matter. So these strange particles were strange in the sense that given their mass, high energy, they had a much too long lifetime, and we understood long after that's because they have a strange quark in them, and that changes the properties. So anyway, all this was fantastic, many Nobel Prize on the way, but that's still says nothing about the nature and origin of the cosmic rays themselves. You would have to access the primary particles, and for this you need to go to space. Of course, we went to space, and now we know better. But along the way, I need to mention the discovery of particle showers. So in the 1930s, people started to work on these cascade reactions, interactions of energetic particles, where you have, so here you have in a cloud chamber, on top you have one particle coming, then there's a piece of lead in which the particle interacts and creates many secondary particles, and each of them are still energetic enough to produce even more and even more, and so you subdivide the initial energy into many secondary particles. And and then Pierre Auger discovered what we call the cosmic showers or atmospheric showers. So he was puzzled by the fact that detectors of cosmic rays on the ground had some coincident clicks, if you like. They detected events much more coincidentally in time, more often than you would expect from simple random coincidence. And he understood that there are actually showers developing in the atmosphere where you have one very energetic incoming particles which produce a lot of secondary particles which hit the ground on a large surface. And of course, the detectors click together, coincident in time. And he was clever enough to try to understand the energy of the incoming particles by looking at the density of particles on certain area, and looking at the energy of individual ones, putting some lead to see how many were stopped and so on. So that's quite clever. And he ended up with the conclusion that the incoming particles are at energies larger than 10 to the 15 electron volts. That's 1 million times the rest mass energy, which is absolutely crazy, and which is still much, much larger than what you can reach in CERN right now. So I'm sure you're all familiar with the Lorentz factor. I don't have to explain these relativistic effects of time dilation and length contraction. At half the speed of light, you have a Lorentz factor of 1.15, and it increases at 99% of the speed of light. It's 7 roughly, but these particles have Lorentz factors of 1 million, which means that in their rest frame, 1 second of the rest frame is 3 weeks in our time, and 1 kilometer it turns into 1 millimeter, if you recall these relativistic effects. So that's very intriguing indeed, and that in the cosmos you can have such high energy particles, again much larger than in terrestrial accelerators. So cosmic rays are not just a nuisance for human activity in space, they're also very stimulating, and they are a mystery. And so one could think that we don't care so much. Actually, we care a lot, in the sense that these cosmic rays play a major role in galactic ecology, if you like. The energy density of the cosmic rays in the galaxy are similar to the stellar light. It's about 1 electron volt per cubic centimeter, and it's also the same energy density as magnetic fields. So they are so important as a component of the galaxy that they play a role in many, many very interesting processes, like thermal equilibrium of the interstellar medium, equilibrium between different phases. You know, there are molecular gas, atomic gas, all this kind of hot, cold, dense, not dense. They also ionize the interstellar medium, and as such, they regulate a lot of things like astrochemistry, or they're also building up the magnetic fields, many things, and they're also responsible for nucleosynthesis of the light elements. Very important things. It's also important for humanity. You know, it's not good for health to be radiated too much, and astronauts know that. And yeah, we use also carbon-14 for dating in archaeology, and this is all thanks to the cosmic rays. Anyway, a lot of things. The problem is we still don't know where they come from, and that's a bit frustrating. And of course, we don't know where they come from for a very simple reason, which is we don't see the sources because these particles are charged, they are nuclei. And as being charged, they are deflected by the magnetic field, so they don't point straight to their source. If you see a cosmic ray coming from here, maybe the source is at the opposite place. So the sky is fully isotropized. I mean, the distribution of these cosmic rays is isotropized by the galactic magnetic field. This picture on the bottom left is actually a computation, but I could clearly have drawn it by hand, just, or little children could do that. Anyway, so when you have, so we are in a mist, it's in the fog, it's quite clear what happens, and here is a very high resolution of the sky seen in cosmic rays, every direction looks the same. So you don't see sources, you don't do astronomy. So that's the problem. So how to get out of the fog? One solution is to turn these cosmic rays, which are charged, into neutral particles, and that could be neutrinos or gamma rays. And this is indeed how we proceed. We see high energy particles in different types of sources because they produce secondary particles, mostly photons, which come to us. The other possibility to get out of the fog is to increase the energy, because the higher the energy, the smaller the deflections. So if you could have enough high energy particles, high enough energy particles, you could start to point to the source and start cosmic ray astronomy. And this is the point. So that's why a real quest of the highest energies has been started. And what we discovered is that the huge energies discovered by Pierre Roget are still too small, despite the fact that they are very, 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 very energetic. There is one vary for each order of magnitude, so that's indeed 1 million times the rest mass energy. This is a huge Lorentz factor, but still, in the galactic magnetic field, these particles have a gyro radius of 1 light year, which is just so small. So they are completely isotropized. Even at 10 to the 15 electron volt, they're completely isotropized in the interstellar medium. So the question is, are there cosmic rays with even larger energies? And the answer is yes. And I pointed here a cosmic ray discovered, observed in 22nd of February 1962, which is very, 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 very energetic. So it's a Lorentz factor of 10 to the 11. And the time dilation and length contraction is such that 1 second of their race frame, in their race frame, is 3,500 years of our time, and the distance between the Earth and the Sun is brought down to 1.5 meter. That's really amazing. I mean, we all understand relativity, but it's good to realize the order of magnitudes we are talking about here. And actually, in 1993, an even 3 times larger energy was detected. Oh yes, and also to go from the Earth to the Sun, it takes 5 nanoseconds of their time, not 8 minutes. Wow. Anyway, so the point is that, first we, with a lot of imagination, we call these cosmic rays ultra-high energy cosmic rays, and probably they should get us out of the fog, and that's the point. Plus, we can, with these particles, explore new physics far beyond the reach of the LHC. And so this brings us back to fundamental physics as well that could be done with these particles. Okay, and there are a lot of things to explore in fundamental physics once we understand where they come from. Unfortunately, these particles are not only very, very, very energetic, they are also very, 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 a lot of times, 32 times rare. What I mean by that, so there are 32 orders of magnitude between the flux of cosmic rays, the standard cosmic rays that we deal with around 1 GeV, and these highest energy particles which reach energies beyond 10 to the 20 electron volts, 32 orders of magnitude. That's with a very continuous spectrum, as you can see. This is truly amazing. Because this is a spectrum which is out of equilibrium, so the universe is producing it all the time. You know, these particles lose energy, but all the time there is this out of equilibrium spectrum which is produced extremely irregular, over 12 orders of magnitude at least in energy and 32 in flux. That's really a wonder. Anyway, so if you look at the flux at the highest energy, we are talking about 1 particle per square meter per billion year. So it means if you have a detector of 1 square meter, which is already quite good, you have to wait for 1 billion years to see one of these particles. That's crazy. And so we need to build detectors of several thousands of square kilometers. And this was actually done. And this was done on the ground. So of course, we use the property of these showers. So these particles arrive in the atmosphere and produce hundreds of billions of secondary particles which cross the atmosphere at the speed of light and spread over a large region on the ground. And if you put detectors in this case, every 1.5 kilometer, you can detect these particles and try to reconstruct the showers that produced it, the energy, and the direction of the particles. And this works very well. This is the Pierogi Observatory in Argentina. I was there last week, actually. So it's still active. It started in 2000 and took first light in 2004. And there is also a second way to detect these particles, that as they cross the atmosphere, they excite the nitrogen molecules, which de-excite emitting fluorescence light. And if you are in the dark, far from the cities, at night, of course, with no moon, you can see this track crossing the atmosphere at the velocity, the light velocity essentially, and detect these particles over very, very large distances. So this is a fantastic observatory, actually, but the main thing that we discovered is that it's not big enough. And because one of the big discoveries with this observatory is that the highest energy cosmic rays are actually charged particles, of course, cosmic rays, but heavier than protons. And the deflection in the magnetic fields are proportional to the charge. And so, if a protons can be deflected roughly about 2 degrees, of course an iron nucleus would be deflected by 52 degrees. So if you have many sources, they overlap. So what you want to do is to go at even higher energy and accumulate much more statistics to start to distinguish the sources, the individual sources, if possible. But it's already covering 3,000 square kilometers on the ground. How can you do bigger? You cannot. Well, some people still dream of extending to 20,000 kilometers on the ground. This becomes crazy. There are already 1,600 detectors deployed in Auger, and to maintain, that's kind of a nightmare. So the solution is clear. Go to space. Well, it's clear, actually. This is what we believe. A large collaboration is believing that. And so the idea is that you can go in space and observe the showers from space. So contrary to what has been the history of cosmic rays, that we accessed only secondary particles on ground. We knew nothing about cosmic rays, so we had to go to space to measure them directly. But now we go to space actually to look down to the Earth and see these showers from space during moonless nights. And we know it works because we started this program of developing an extreme universe space observatory, EUSO. So there's a history of that. So the first idea to go there dates back from the late 1970s, and then there have been several proposals. A major step was the proposal of EUSO to ESA. So ESA played a very important role in this history, and so the proposal was submitted to ESA in 2000. And then there was a phase A, which was successful, I heard, but then the phase B was postponed and there was no funding, so it has to stop. Then there was a revival with JAXA, hence the full name now EUSO, where GEM means Japanese Experiment Module, so it was due to go to the Japanese module on the ISS. And so it was going well. Unfortunately, there was this Fukushima disaster in 2011, and JAXA disengaged as a lead agency. Of course, they are still there and funding the the Japanese work packages and so on, but then we have no full mission since then. But ESA's interest remains, so we have the topical team on ultra-energy cosmic rays, and the different nations are funded by their national space agencies, so the story continued, and we are now the EUSO collaboration renamed as joint exploratory missions towards an extreme universe space observatory, and we did a series of experiments just to improve on the technology, to demonstrate the technique, and reach well, the highest TRL for this kind of missions. And now we're essentially ready. So we already demonstrated the relevance of the technology and its performance. So we had a series of missions. The first one funded by CNES, well, by all the agencies, but led by CNES, let's say. In 2014, we did the first balloon flight. And then, okay, we also have an instrument on the ground, EUSO TA, on the site of telescope array, for those who know. And then we had the first super pressure balloon flight with NASA in 2017, and then we launched to the ISS. So currently we have an instrument on board the ISS, which was launched in 2019. And then we did last year another super pressure balloon flight with NASA. Unfortunately, it was supposed to stay up to 100 days, but there was a leak in the balloon, so we dropped into the ocean after less than 2 days, so that's unfortunate. Anyway, and now we are going for the final balloon super pressure again in 2027. So so this is the program that we develop. I don't have time to go into details about all these experiments and what we learned at each step. So maybe it's a good occasion to remind that ballooning is very interesting to get much more ambitious projects started and follow up on the technology and things like that. So I will just show, so yeah, this is what I like to call the stairway to heaven. We have several steps, and but of course we want to go for a full-scale mission in space. So we develop instrumentation. So the idea is to look at these showers in the atmosphere from essentially the ISS, or let's say low Earth orbit. So you are, let's say, 400 kilometers away. So, and remember that the light that you want to see has been created by one particle arriving, one cosmic ray. It produces many secondary particles that excite molecules, which they excite, and you see isotropically, and this is the light that you see. So it's very indirect, but it works very well on the ground. This technique is fully mastered, and we reach very high precision. High precision means 10% energy resolution, which for astrophysics, for this kind of study is more than enough. And so we simply want to put that in space, but so we are very far from the shower. We need very large optics and very sensitive detectors, so we use photomultipliers. We also do Cherenkov camera. Don't have time to go into the details, so we developed our own electronics and so on. I have to skip that. So these are the three photo detection modules with 6,000 almost 7,000 pixels, and we are doing photon counting. So we are counting photons one by one because there are not much to detect. We are doing precise calibration. I go fast. This was the EUSO balloon, the first balloon flight. Okay, I go quick because okay, this was supposed to be a video of mini EUSO. Let me yes. Okay, but it will be too long. Anyway, this I don't know if I can quickly go through the video. No, I cannot. Never mind. Okay, okay, thank you. I don't want to. All right. Anyway, so yeah, so this is mini EUSO. So mini EUSO is a very important step for us because not only so it operates in the ISS. So of course it demonstrates the robustness of the technology and its performance. It's a good way to show how these things work. But also it allowed us to explore the multidisciplinary objectives of the GEM EUSO program, let's say, because again we are going in space to look at the atmosphere to see cosmic ray showers, but there are many other things occurring in the atmosphere. You have meteors crossing and leaving tracks, so it's just like a track of cosmic ray, except it's much slower. They don't go at the speed of light, and but it's still the same type of idea, and we are also looking at transient luminous events occurring in the atmosphere. So we operate with mini EUSO at 3 different time scales. Our basic time resolution is 2.5 microseconds. So here you have a plot showing on the x-axis is the time scale, on the y-axis is the number of counts that you expect, and you have all sorts of different things, lightnings, clouds, different types of Earth emissions, also waves like tsunami waves in the air glow, in the night glow, which are potentially very interesting as well. Meteors, and we are looking also for interstellar meteor, which is a very active field for other communities. And okay, a lot of things that can be done. So our basic time resolution is 2.5 microseconds. Then we have a first integration, 128 times of that, which is, so let's say, a third of a millisecond. And then we operate also at 41 milliseconds, where we have continuous monitoring of the atmosphere with absolutely unprecedented capacity. We have a pixel resolution on ground roughly 5-6 kilometers. And we also, and this is in UV, I did not say it. And we have a monitoring of the Earth. We have imaging, I said with 2,300 pixels in that case. And this has never been done. I mean, looking at the Earth in UV, nobody does that because the Earth is not emitting much. So there's a lot to discover. And indeed, we actually drew the first sky maps. So these are different passages of the ISS. When we turn on the instrument, it has to be turned on by the astronaut. This is what the movie was showing. But anyway. Yes, so actually you can find these maps now. We've published all this, of course, and you can find these maps in the Google Earth format. They are included there. Anyway, so okay, we can see different types of clouds in UV. Again, this has never been done because we really count photons one by one, and we typically have 1 photon on average. The background for Earth at night is typically 1 photons per unit time. In our case, it's 2.5 microseconds. We see different types of activities. Yes, I showed here on the top left, top right, some fishing boats, people fishing with lights during the night. That's probably not good for the fish, but anyway. So here comes another thing that we were able to calibrate fully mini EUSO to fully, so we have calibrated flashers on the ground, which we flash when the ISS passes over. So we know exactly how many photons we send, we know how many we count, and then we have absolute calibration, which is quite nice. And this allows us to confirm the efficiency, the detection efficiency, and confirm the capacity of detect the showers, and this is fully consistent with the simulations. Anyway, let me go fast now. So here you see different types of events, flashers on the ground, so you see them moving in the field of view, that's on the left. On the right you see, of course, clouds, so there is a lot of monitoring you can do. In the central picture, you don't see it very well. This is actually the reflection of the moon on the Sahara, which I find cool. We don't learn so much with that, but anyway. And now here comes the elves. So we can see elves. So I don't say much about elves because, of course, Thorsten Neubert will discuss that much more, since that's one of the main objectives of the ASIM mission, also on the ISS. So we definitely have joint observations, even though we did not exploit them yet. These are, so you have electric discharge, which produce come and kind of destabilize the ionosphere, and you have this spherical wave that meets the ionosphere. So you have, I would need my two hands to show, but you have this concentric a circle expanding. So we can see that in the field of view, as you can see that, and we can see several concentric circular waves across, propagating over huge distances, hundreds of kilometers. So this is the type of analysis that we do. You can see, it's a bit difficult, I cannot point, but anyway, in the bottom center panel, you can see the intensity integrated, so as a function of time, the intensity in a given radius. And you see this ring expanding as a function of time. There's a lot of things we can do. Actually, Zbigniew Plebaniak, who is going to speak about strange quark matter later, is actually the one who did this analysis. You can see here that we can see several different circles in the bottom panel. So you can see actually up to 5 elves, or five circles in the same elf, some of which are consistent with reflection on the ground of the initial electromagnetic pulse. I think I need to go very fast. So these analyses have just been submitted. Well, the paper has been submitted last week. So there will be more to talk another time. We also do meteor observations, and this is very important. We have more than 24,000 candidates of meteors. Not candidates, actually, they are meteors. And we can, and this is the first systematic detection of meteors from space, and there's a lot of things you can do from space that you cannot do on the ground. So we also published this year a very extensive paper on the meteor analysis, which bring really new results to this community. So this is just an illustration. I could speak about the limits on dark matter, and then the second flight that drop in the water. I just go quick. Yes, and this is our future. Let me just finish reminding. So our goal, again, is to measure cosmic rays, the ultra-energy cosmic rays. They are so important. This is really one of the 4 pillars of multi-messenger astronomy. We need to get to these particles. They will teach us a lot about the most intense phenomena in the universe, but also about high-energy physics and fundamental physics, because they are so much far beyond what the reach of LHC. We have this program, this Stairway to Heaven. Each step we learned a lot of things. Now we are ready. We demonstrated the capacity of detecting these showers. And so this was, this is the EUSO was a mission that from the Russian Space Agency, and ESA was going to take part in this as a mission of opportunity. Unfortunately, Russia's military invasion of Ukraine put an end to this beautiful project. But I mean, the idea is still there, and I hope we can do something in the very near future. So last comment, the technology developed is very efficient and versatile, so we can do a lot of other things than cosmic rays. I illustrated that with elves and meteors. But essentially we have huge exposure at the highest energies from space. And so what did I want to say here? Yeah, so a lot of synergies. So we actually submitted with Torsten some years ago and Maria Gricevich from the Meteor community a synergy project to ERC. We were not funded, unfortunately, but I raised the question mostly to ESA about the funding scheme, how to constructively assert the cross-disciplinarity of this kind of projects, which may not be enough to be funded through one community, but when it serves many different communities, how can we put this into place? This is an open question, and I should definitely stop. Sorry for being long.
Thank you very much, Etienne. Everything very, very interesting. I think we are over time, but if there's just one quick question, I'm happy to take it. Christophe.
Thank you very much for this vast panorama, of what you can see from space. So ultimately, you insisted a lot on the highest energy particle. So in EUSO, from space, you say we will look down towards the Earth and see the shower, but how? Because you have in space, we will have a relatively small area, right? So what is the probability of detecting from space, on the ISS, a 10 to the 20 EV particle with the limit of current technology,
Yeah, so actually the idea to go to space is to increase the area in the sense that we use either Fresnel lens. In the case of mini EUSO is Fresnel lens. In the case of Poema design is a mirror, but with a very large field of view, like plus or minus 30 degrees. So from the ISS, we cover 200,000 square kilometers of atmosphere from there. So,
but Fresnel lens, not in the UV, right?
Yes, in the UV.
In the UV, wow. Okay.
Well, yeah, this is Japanese technology. Yes, and so you can have a huge aperture. So the only thing is that in the case of mini EUSO, we are limited to the size of the UV transparent window, the quartz window in the Russian models, and so the optics is 25 centimeters. So our energy threshold, so it means we don't collect so much light. So our energy threshold is 310 to the 21 electron volts. So there are no cosmic rays at this stage, so we cannot see them. But if it's really geometric. If you increase from 20 centimeter to 2.5 meter diameter, which is the project, then you lower your threshold by 100. And that's it. And so we know exactly how it will look. We see the light showers, so we have flashers which reproduce the profile, so we know how it works. And indeed, there will be a lot.
Thank you.
Thank you.
Sorry for being long.
No. Everything very, very super interesting. Thank you very much. Let's thank Etienne again. And next speaker, we move to Torsten Neubert for the report on ASIM.
Thank you. Oh, it's on. Good. Thank you very much, Etienne. I think this was a very interesting talk you gave. Even the introduction put a lot of things in place for me. So thank you for that. Also, let me start out by saying that we do see, of course, a lot of elves, more than maybe mini EUSO does, but you see more meteors, which we also observe. So we should talk, yeah. In any case, I will talk about the Atmosphere-Space Interactions Monitor, and first I will show you some slides about the instrument, so you know what it is that we measure. And then I'll talk about some of the science that we do. We have a lot of different topics that we can go into, but I've selected 3 that I think are sort of the general overview of the main topics that we investigate, and then some lessons that we've learned from running ASIM on the space station. So. to let you know what we are talking about, here's ASIM on an external platform of the Columbus module. And you will see some packages, instruments, boxes looking down towards the atmosphere, some computers, and what we are looking for are these TLEs, as you referred to, transient luminous emissions, that are basically lightning effects up in the stratosphere, mesosphere, also in the clouds, of course. We see that because we look nadir. Think about, okay, look at the right. You have the electron density. It's going up as you go up in altitude because we approach the ionosphere. So think of the ionosphere as a good conductor, and you have the ground below. It's also a good conductor, and then you have the clouds, where convection is charging up the clouds. So that's kind of the batteries, and lightning is simply short circuits in the batteries. So they can short circuit internally between positive and negative charge regions or to the ground, or, as it turns out, up towards the ionosphere. So you'll see a blue lightning or blue jets going upwards from the top of clouds, the wrong way, so to speak. There's also sprites that you may have heard about up in the mesosphere, and then the elves that Etienne was talking about. And I'll get more into elves in this presentation here. And then the gamma rays from the terrestrial gamma ray flashes discovered by accident, you could say, looking towards the cosmos for cosmic gamma ray flashes. They found these flashes when they passed over thunderstorm regions with the Compton Gamma Ray Observatory, the BATSE instrument. So what we are looking at then is, you know, things in the clouds, top of the clouds, of course, and then up in the stratosphere and mesosphere. So the instruments are shown here, and on the left you have the optical instruments. So that's 2 cameras and 3 photometers. It's not very fast frame rates. It's 12 frames per second. But we get 400 meters resolution on the ground, and we look at 2 bands. One is the blue band, we call it the 337 nanometer, and the other is red at 777 nanometer. 777 is a usual line that the new geostationary lightning mapping instruments are using. So we have that in common. The photometers, on the other hand, the 3 photometers, have very high sampling frequency, so we get 10 microsecond resolution. We have the UV and the red and the blue band. And I should point out here that the UV, because the atmosphere is absorbing UV quite a bit, okay? And we would like to see the difference between what is emitted way down in the clouds and what is coming up to us let's say, from above the clouds in the stratosphere and mesosphere. So the UV is very sensitive because of atmospheric absorption, but it's a very interesting instrument for us because it can tell the difference, maybe, sometimes at least, where the emissions, how the altitude of the emissions, basically. Okay, so the X and gamma ray sensor, there's a low energy detector and a high energy detector. And we go up to 40 MeV, which we think is a very high energy, but it's not very, 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 very high. I mean, I can't believe these orders of magnitude you have. But I should say that it's the highest energy we think that is naturally created in the Earth's environment, all right? So for the low energy detector, it's pixelated, and there's a coded mask that creates sort of penumbra pattern on the detector plane, and that allows you to determine where emissions are coming from if they are a point source. Okay. So let's first look at just the basics. How does lightning look when we see it with ASIM? So on the left, you have the red band, and on the right you have the blue band. And it's just, you know, a circular thing. We just repeat it. It's, I think, 5 to 8 frames. I forget how many frames. There's a little bit difference in it. That's because of scattering is different in blue and red. You will see here what we find is lightning at the cloud turret, a top that is sticking up above the main layer of the cloud. So you see actually lightning inside the cloud and then reflections on the lower lying tops of cloud surrounding. So this is called the cloud turret, which are really interesting, as you will see for us in the science context that we are looking at. So, but it also tells us that we actually have a kind of an X-ray of clouds, which we think is really interesting. Using lightning as a source, X-ray kind of source, we can say a lot about the density of clouds and with a much higher spatial resolution that you will see from other satellites. So, so let me talk first about ELVs and a little bit more about the scattering of photons in clouds. Now, you have the image in one of the bands, I forget which one, and then we have the photometers, and I can't point, but you can see the gray curve is the UV, and it has a very fast rise time. So that tells us it's not affected by cloud scattering. So it's coming from above the clouds, okay? And the red and blue curves, they have a slower rise time, so they are lightning inside the clouds, all right? Now, the way this is understood is that the photons, they are created inside the cloud through a lightning strike. They are scattered, and they reach the detector with some delays. But the UV is actually emitted at this yellow thing, which is supposed to be at the bottom of the ionosphere, okay? That is created by radiation, electromagnetic radiation, emitted as a pulse at the cloud discharge. It's traveling unaffected by scattering up to the ionosphere, where the electric field is accelerating the free electrons, and they hit the neutrals and they excite them, and you have optical emissions. But it's only in a thin layer, because if you go too high, then the field is shorted out because the ionosphere is conducting. If you go too low, then there's not that many electrons. Okay. So as a pulse is coming up, it's reaching the ionosphere and spreading out like a ring. Okay. Right, so just to give you a number, we have observed something like 10,000 ELVs, roughly speaking. And the reason why we see them is that the UV photometer is very, very sensitive, because it has a larger aperture. So what you see on the photometer plot is actually engineering units. It's counts, okay? So the real UV pulse is not as large as the optical pulses, but because you have a higher aperture, larger aperture, the counts are, in this case, you know, close to the same thing. So the first study that we threw ourselves at has to do with the TGF, where we saw TGF at the same time as a lightning generated an ELV. Now you have to understand that one of the motivations for ASIM is to understand the physics behind the generation of TGFs. TGFs was the terrestrial gamma ray flash. This up to 40 MeV sudden bursts of X-ray and gamma ray photons. So what is actually the mechanism behind it? Is it large-scale electric fields in the clouds that suddenly discharge, or is it associated with lightning and lightning propagation? And you can see here that it's the latter that we identify with ASIM. So in this plot, the let me see, the black outline is a section of the full field of view of ASIM cameras, okay? The bluish line coming down is the ISS orbit. I think the ISS is shown somewhere as a red dot here. And then you see a smaller section here. This is the cropped images of activity that are downloaded to the ground. The colored map that is the basis of this plot here is from a Himawari satellite, and it shows the cloud top temperatures, which we have translated. Have we translated to altitude? Maybe we, yeah, I think so, didn't we? Yeah, cloud top, yeah. So, so the region where we see activity is where the clouds are really high up. Okay, so that's a cloud turret I showed you before. And the white circle thing around is the X-ray instrument probability map of where the TGF is coming from. And here we zoom in and we see that the image from the camera is then matched with the black dot, which is a ground-based observation of lightning at that time. Now, what is the attitude of the instrument? I mean, this is not always simple when you sit on the ISS because it's a huge structure. And we don't have independent on the payload measurement of time and attitude. So exactly where are we pointing? There's some uncertainties in it. But we use ground-based observations to try to match time and, and try to correct for, you know, the direction that we are pointing. So in this case, we show here on a logarithmic scale the calibrated fluxes of the 3 photometers. And you can see that the lightning is sticking out there, and you also have a very strong signal in the UV photometer. If we match it up, zoom in, and put the X-rays on here, the X-rays are coming, the flash, the TGF is coming right at the center, right at the beginning of the event. However, I have to caution here because while the relative timing between the two instruments are kind of okay, plus minus 5 microseconds, there's scattering in the cloud, so exactly what comes first is a bit difficult to say, but it's suggesting that the TGF comes first here. And here's again the idea that you have an intercloud discharge that radiates electromagnetic pulse upwards, generate the ELV, and then you get the fluxes up to the ISS. Can I run this video from here, or no? Or can you do it? Down below at the, yeah. Okay, so here are the X-ray photons, and here are the ELVs, and we have put in, run it again, please. We put in the reflections that you were talking about, Etienne. The reflections of the electromagnetic pulse in the ground generate your successive ELVs expanding out. So this was quite new, and not to brag, because I'm not that kind of person, but nevertheless, I think you should know that we hit the front cover of Science within 2 years of launch of the satellites, which I think was really, really, really good. And to summarize here at this point, so 10,000 ELVs because of the UV photometer. We observed about 2,000 TGFs. And the reason we have such success here is that the instruments are designed specifically to look for these kind of things. Yeah, okay. Which was not done before. Lightning emissions, that should be microseconds, not milliseconds. And the new physics comes from simultaneous and accurate characterization of the lightning and the TGF. That is the main essence here. So, okay, so we have made many follow-up studies, and not so many with ELVs also, but what I would like to address is what comes first, the TGF or the optical pulse, all right? See, if the TGF comes first, maybe the TGF conditions the lightning, the optical pulse, basically. If the optical pulse comes first, maybe it's a potential charge that is springing up, and then it's creating an impulsive high electric field that generates the TGF. So it goes to the heart of what is actually the mechanism of TGF generation. So it's an important question. And here just the event that we've picked out. And we found a very long duration TGF, very strong and very long duration, so the time scales are long. Okay, so here we see that the TGF starts well before the optical pulse, right? This is a conclusion of this paper, which was just approved, actually just came out in the GRL, I think, yeah. So we find the TGF comes first. Question is, this burst of high energy electrons and gamma rays, is that what conditions, helps this current pulse to come along, okay? And once the current pulse comes along, does that then stop, short circuit, basically, the TGF? Now it can't run, that stops the TGF, okay. So this is kind of interesting things that came out of this paper. All right, so that was one of the three aspects that I thought I would talk about. The second are the blue discharges. So you notice that the ASIM has both camera and photometers at 337 nanometers, which I call the blue. And that's not commonly been flown before in space. And it's interesting because it picks up what's called streamers. We call it streamers. You see them here on the ground, in for example, high power systems. It's just sizzling, it's not like a fully developed discharge. That's a streamer thing, and it's bluish. When you watch lightning coming down, you don't see it because it's ahead of the tip of the lightning. The main lightning is called a leader, and it's very bright optically, and very bright also in 777. So the thing, though, is we are looking down towards the Earth, so we don't really have good altitude resolution. However, we did find an event that looks like this in the cameras. So you can see it's elongated, and the arrow shows the direction to the ISS. So if you have a camera that's looking down at the edge of the field of the view, there's something sticking up, yes, then you will see it sort of elongated in that direction, away from where you are looking. So that tells us, for example, the middle image is very clear, that we have something that is sticking up outside and upwards over the clouds. And if we look at the photometers that are shown below, they show very, very clear signatures in the blue. We have very little in the red. And we have interpreted this as a blue jet, actually a pulsating blue jet. You can see two peaks coming up. If we zoom in on the very peak of the very first peak here, it looks even more dramatic. Here the tick marks show 1 millisecond. And so the blue peak rises extremely fast within one sample, okay, 10 microseconds, which tells us that it is at the very top of the cloud because it's not affected by scattering. There's also a small UV signal, which tells us that this brief event is strong enough to generate an ELV in the, in the ionosphere above. So, and again, I was debating with myself if I should show this slide, but because I don't want to brag, I don't, yeah. But we actually made the front cover of Nature. I can tell you at home, at my institute, they were really happy with this because, and I was relieved. For quite a bit, for quite some years, I've been, let's say, I don't know what it's called in English, but it's okay that I came out there, but people didn't really want to talk to me because we had big cost overruns, okay? Yeah, so it was an expensive experiment for the Institute, so I was kind of accepted, tolerated. I was tolerated, okay? But after these papers came out, things loosened up a bit and people were more, you know, friendly, you could say. Okay, so we have tons of blue discharges and good time resolution, space resolution, and the new physics here are the different bands that we look at. Yeah. Okay. Some follow-up studies. Yes, we found that these are related to electromagnetic signatures called narrow bipolar events. The thing is that the community of electromagnetics measurements of lightning, they see all sorts of signatures in different bands, and they give them names that show how the signature looks like, but it doesn't say anything about what the process is. Okay, it's a type K event, or it's a narrow bipolar event, but they don't really talk about what it really is. So it's helpful, I think, that we can couple electromagnetics with the optical emissions here. So it's a fast discharge. That is what we are thinking. Now, we've seen many of these, and here's a global distribution. And what we are thinking to do is to see how is the climate connection, because these are at the very top of clouds, and what do they do to the atmosphere up there? Okay, they stick into the stratosphere even. So will they eventually do something to the atmosphere? That's interesting. So it's put into some models showing that they will increase, the prediction is 3 to 13% increase per degree Kelvin. That's what, if you parameterize it with things that go into climate models and then run the climate models, this is what you come out with. Now, we actually also entered a third time this in one of these high-level papers, Nature here, and that's the cosmic gamma ray. So even though we're looking down at the Earth, we can also see gamma rays coming from the universe. Okay. Now, ASIM itself is interesting in this respect because we have very high time resolution measurements during the main phase of some of these events. So what we can see is oscillations, quasi-periodic oscillations in these gamma ray bursts that where other instruments like Fermi satellite that are saturated. And there's more studies looking at GRB, cosmic gamma ray bursts. So I have 3 lessons. One is that just looking at this picture here, ISS is incredibly complex. I mean, it's just, if you just sit and look at this and ponder, it's just totally amazing. But I think, though, in spite of this, it has been it's been a good experience to be on the ISS. I mean, I'm not going to downplay the problems and issues that you face when you try to get something up there, but given the complexity, I'm actually quite pleased with how things have been going, especially somebody else wanted to use our payload, our platform, so we couldn't stay there for more than 2 years. We were moved to a different platform that was vacant. And then when this other experiment was done, we were moved back again. I mean, I think that's pretty cool, you know? And I guess this is good to be able to do this, where if you want to go to the moon and Mars, you know, have that kind of flexibility. So this is where we were in a temporary position during about 2 years. The second lesson is it's been very valuable to have interactions with astronauts. And in our case, it was a Danish astronaut, Andreas Mogensen. For example, in one of his missions, he has been there twice, he took these images, so that's consecutive. The first is not a consecutive image. It's just to show the main cloud turret. And then you see a blue lightning coming up at the top of the cloud. This kind of image, which is at a slanted view, helped us to understand the ASIM data. So that was very valuable. And the third lesson is that the ISS orbit is perfect for thunderstorm studies. We cover all the regions, all the main regions, 51.6 degrees south and north. We are at the lowest altitude you can get, so we are close to what we want to measure. So it's actually extremely good for this kind of studies, okay? Some of the things, the green ones, we had success with, but sprites, blue jets, etc., are difficult because of lacking altitude resolution, right? And we've shown, though, that there's been tons of blue activity, much, much more than what was expected. So we would, of course, like to observe that more in the future with future experiments, if possible. All right, that is all I have for you. Thank you very much.
Thank you very much for this beautiful presentation, really.
Thank you.
And it's a pleasure to see things going up there, working,
Yes.
delivering nice science. It's
Yes,
fantastic, isn't it? Christoph.
Thank you for this very exciting talk and a long list of nice new results. So you're saying that there is, at the end, a poor altitude resolution. So how will you fix it?
We can't fix it as such with ASIM.
With ASIM, but maybe you could use a combined ground and space data with a good clock synchronization so that you could hope to make time of flight or sort of, you know.
You know, we can do, not in general, but if we are lucky to have ground-based and space-based at the same time, this is what we're looking for. Mm-hmm. Now, we try to galvanize the community, and there's many that take observations at night. There's this whole meteor community that observes the sky. And we almost had a case with the sprite and from space, ASIM, and from the ground. But the data stopped. "30 milliseconds before the event." There was a gap in the data, our data, because it has flown over, I think, Houston or something, couldn't download the data. The buffer was full because there was thunderstorms over Houston. I forget the story. We have hardly any data gaps in the ASIM. Okay, it's very rare, but 30 milliseconds before the first and only so far event, the data was lost.
If I may ask a second question,
Yeah.
what is the rate of expansion of the ELF? the radius, what determines this velocity that you've shown? Yeah.
Well, actually, the visual velocity is faster than the speed of light. But it's because
No.
no. Think about it. Okay, the pulse comes up with the velocity of light. Okay.
Yes.
And then you hit the ionosphere. The pulse comes up here, and then as it travels a little bit further, okay, the edge of the pulse is already out here. The photons are not traveling faster than the speed of light. But it looks as if, Yeah. It's a geometry, yeah. But it's the speed of light that determines it, yeah. Yeah.
Thank you.
Very much. Let's thank
Thank you very much.
the speaker again. And the last speaker of this session is Zbigniew Plebaniak, and he will tell us about the experiment Strange Quark Matter on the ISS.
Thank you very much. So my name is Zbigniew Plebaniak. I will say about searching for massive non-relativistic objects with this proposed experiment SQM ISS. And I'm giving this talk on behalf of the SQM ISS group. Maybe it can be a bit strange talk because I will say about things which are hypothetical, and we would like to measure with the detector which is not built yet. It's under construction. So I would like to try to give here some introduction to the topic. The content about our detector will be just the final part of this presentation. So let's start with an introduction. What is SQM and why we are interested in? So from standard model, we know that we have 6 types of quarks. But if we look on ordinary matter, we know that it's composed of protons and neutrons, which contain only 2 types of quarks, up and down. And the rest doesn't exist in matter around, let's say, in ordinary matter. But the idea is if we add the third quark, the strange quark, in some specific conditions, it can create also stable matter. But to do this, we need those specific conditions, what means extremely high temperature at about 10 to 12 Kelvin. We need extreme pressure at about 10 to 35, 36 Pascal. And analyzing models already developed based on data taken in CERN and based on other accelerators, everything seems to be consistent. So we have prediction that this kind of matter can exist and can be stable. One more thing is that to make it stable, we need to put inside much more matters, much more quarks inside. So if we assume that 3 quarks, U, D, and S, will be equivalent of 1 baryon, we need amount of matter in order of 100,000 and even more baryons to have it stable. And then here I put some key points, maybe the most important works in development of modeling of strange quark matter finally, but the most important was development of mid-bug model at Massachusetts Institute of Technology, and this provides us framework to describe hadrons as quark containing bugs, and then the rest was kind of continuation development of this model. And another very important work in this context is 1984 by Witten present a cosmological scenario for stable quark nuggets as a dark matter. So it was proposition that quark nuggets, what means a strange quark matter, could be a good candidate to explain dark matter mystery. And what is really interesting and important also here is that everything is consistent with standard model and what we know already about interactions. So we don't need the new physics. We just need those specific conditions to make strange quark matter stable. And if we look on the plot on the right, here we have energy per baryon as a function of strange quark mass, which is parameter in this model. And in the red area, we marked the area where potential SQM would be stable. So it means when energy per baryon is lower than around 930 MeV, what is more or less the equivalent of proton or neutron. It's around. So everything above is unstable, and if you look on the masses of particles containing strange quark, they are reaching 1,000 and more and are unstable, are decaying. But below, if we could create this matter with energy per baryon below, it should be stable according to models. And this is what we are looking for. As I said, we need more matter inside, so it would be really heavy particles. And additionally, because we are adding strange quark, the total charge would be lower in respect to baryonic number than in ordinary matter, what means interaction will be weaker. So we have more dense matter, less interacting, and really, really heavy. What fits well to the hypothesis that it could be a kind of dark matter that we cannot see using standard methods. So it's a great candidate to explain the dark matter. As I said, we need those extreme conditions to create. We can assume that it can be created during Big Bang. It can exist inside neutron stars or during collisions of such heavy objects. Maybe there can exist also quark stars as huge objects composed of strange matter. And according to models, once again, it should be also created during collisions in experiments like ALICE or STAR, but we cannot observe. It may be because of time scale in which we have those enough conditions is too short, and this is why. We don't know. But for sure we are interested in very heavy particles and weakly interacting, which can explain the dark matter. And additionally, if they can interact mainly via gravitational forces, they can be distributed in the universe in similar way to the standard, the ordinary matter. So we can expect that when we are in the Earth, we are crossing the traces of those particles, matter objects with velocity around 220 kilometers per second. So we would look for such kind of particles. And there are many attempts to measure this kind of stuff. I'm not going to describe in details, but we can measure directly when such kind of particle is crossing our detector and can interact somehow, and we can measure the effect. We can measure indirectly. We expect that even with weak interaction, maybe there can be some product of interaction, for example, with atmosphere. So on the plot on the right, you can see two tracks. In the center part of the plot, it's the standard meteor track. So development of the signal is at higher altitude and is really unstable, while the track produced by strange quark matter in hypothesis can be much more stable at lower altitude because needs more dense matter to have possibility to interact, and we could also observe this kind of tracks using detectors for observing meteors and similar things. And also directly we can try to measure some artificial things coming from strange quark matter. For example, we tried in past to analyze moon soil also using seismometers on the moon. I will say a bit about this later. And I will go briefly through a few experiments that try to measure strange quark matter, which are somehow connected with our plan detector to give also the context. So first is Pamela, and this was experiment designed to measure composition of direct cosmic rays. So there was a track tracking the detector and calorimeter on board. And as SQM would have lower than ordinary matter charge, but heavier mass, it could be also measured by this kind of detector. And it should be relatively easy to distinguish the tracks of heavier particles to distinguish between the tracks of those strange particles, strange matter, and standard measured tracks of protons, antiprotons, heavier nuclei. So Pamela measured a lot of particles, but without any significant conclusions about existence of strange quark matter. The next is MINUSO. MINUSO was already mentioned by Etienne during one of previous presentations, and with MINUSO we can measure also meteors, observing the Earth from space. So in the red area on the left, in yellow on the left, you can see a summarized track of one example of the meteors. Then a bit on the right, the consecutive frames with the signal. So this is the way in which we can measure. And in MINUSO we analyzed 24,000 meteors recorded during a bit more than two years. And in this data set, only 3 potentially interstellar meteors with speed higher than or in expected range. We expect that if this kind of object, which can be SQM, is coming from the outside of solar system, the velocity should be higher. It should be higher than around 73 kilometers per second. So we have 3 candidates here, but signal is really noisy, is really weak, and we cannot get any conclusions also from those measurements. However, we measure something like this, maybe more detailed analysis. We are going also to analyze more MINUSO data. Maybe something is there, but by now from MINUSO data we cannot get any conclusions also. Another experiment, DIMS, which is placed in telescope array site, the observatory for cosmic rays from ground. We have there also EUSO TA experiment. In one of DIMS stations is placed in EUSO-TA site, and the idea for DIMS is to use commercial photo cameras with really high parameters, but still commercial, with dedicated readout system, electronics, and so on, to observe sky and observe meteor tracks, to search also for interstellar meteors and similar things. And they, in several months of observations, they recorded a lot of tracks, but also without candidates for strange quark matter. So we don't have any evidences for SQM observing the sky like for meteors from ground. In past we did, it's my mistake, soil spectrometry, and we use seismometers on the moon. So with seismometers, the idea was that there was mounted a network of seismometers on the moon during Apollo missions, and those detectors detected 28 events with strange signal, which can be produced by something heavy impacting the moon or interacting a bit above the surface. We don't have further conclusions. We know just that 23 from them were coming from more or less the same direction, what could suggest potential source. But we discussed coming back to the moon during sessions here previous days. So maybe in future this is also interesting area to think about investigation in SQM direction. We use also spectrometers to test 15 grams of soil from moon to search a specific ratio between charge and number of baryons inside, but also without any evidences for existing. And here on this plot, I plotted many cases of proposed coming from the different model hypothetical particles that can exist. So we have on y-axis the mass of the particles. In GV on x-axis we have speed. And in central part, the green one is SQM, and the speed is related to galaxy bound particles. So we have around 200 kilometers per second, but we can see that the range is wide in masses and in speed, the expected proposed particles. On the right, we have very fast cosmic rays and other things. And two areas marked on the plot, the pink is related to area which can be covered by detection with scintillators, while the blue is for the detection with piezoelectric detectors. So heavy particle can hit and produce some phononic signal inside. So this plot can give an idea how to design the detectors to detect this kind of stuff. And this is our proposition, SQM ISS detector, which can be placed on board the ISS and can try to detect this kind of signals. We submitted proposal to Open Space Innovation Platform, and this was selected as excellent by ESA. And now we are in the phase of realization. And so what is the idea? The idea is to develop the stack of scintillators and piezoelectric plates, we would like to use finally 4 scintillator plates and 3 piezoelectric in between to try to detect this kind of heavy particles coming through. So we should have both phononic and scintillation signal in the same time, using additionally time of flight readout. We should be able to say something about speed of crossing particles and other parameters. Even if we cannot detect any particle, we can set the upper limit for existence of this kind of strange particles. The design of the detector and the background was published in this paper you can see on the screen. We plan to have full redundancy, so we will have main acquisition and spare acquisition with all critical subsystems double, so power, CPU, readout, communication with the station. The funding is coming from national agencies of 3 countries, or is planned. This is in realization, let's say, right now. The 2 leading institutions are in scientific part of the program are INFN from Rome, Tor Vergata, where the manager of the project, the PI, is from, and this is Marco Casolino, and the second, the main, is APC in Paris, France, with Etienne Parisot. And additionally, we have also 2 institutions, satellite, let's say institutions from Poland, currently without tasks during the development or strongly defined tasks, but they plan to be involved in preparation of software, the data analysis, and they plan to participate in next stages. And we already created a laboratory model. So we tested piezoelectric, the response of piezoelectric system. As I said, we will use the metal plates with piezoelectric detectors, 2 detectors per 1 plate and 3 plates in total. And according to the first tests, still without vacuum, the test in vacuum is planned for next weeks. We estimated that we should be able to detect particles from in mass from micrograms, but it can be lower when detector will be mounted on board ISS in microgravity. The response of this kind of the detector will be much better without noises. Of course, it must be mounted in proper way. We are also testing, or we develop and we are upgrading the idea of time of flight and scintillator part. So scintillator plates will be divided in each plate divided in 5 strips with 2 silicon photomultipliers at the end to limit the time in which the signal can travel from interaction point to the detector, to speed up readout. And with this kind of detector, we should be able to detect particles with energy, the mass range between 10 to minus 9 to 10 to around 8 grams. What means that potentially we could detect also primordial black holes passing through the detector, and many other things I did not list it here, but it could be another talk. So this is the idea. According to the scheme, we are working on development, and here is my final slide with the summary. So we are now in pre-phase A, let's say. We are upgrading our laboratory model. It can be transferred to engineering model soon. Of course, we would like to thank to European Space Agency for selecting this project for realization. Without this, it would be not possible, and as I said, with relatively cheap detector, potentially we can cover huge area. So this is really nice, and thank you very much also for the invitation to give this talk. Thank you.
And thank you very much for your presentation. Questions? Christophe?
Thank you for this very exciting and prospective talk. I have just a question about the strange quark matter here. So you said that the energy, I'm not a specialist, but I know some other systems in cold atoms which can make clusters. So you are talking about clusters, essentially, of quarks, which have attractive interaction and a bound state, so that the energy per nucleon is lower than the standard proton-neutron energy, right? And so my question is that if there is one bound state that would lead to stable matter, there might be other lower energy states, which could lead to collapse or, So when you say stable quark matter, what do you mean stable, which means long-lived, extremely long-lived? There is no possibility of decay to make another, lowest energy state?
Yes. So,
so you have this bag model, but,
yes.
but what is the hypothesis behind this bag model?
So the hypothesis is, I think, exactly what you said, that when we add another quark, which is different particle, then further Pauli rule to I don't know if we can display once again the presentation. I have a plot. Okay. So the point is that the quarks can exist here on the white plot. We have potential energy levels for quarks in case of only two quarks, up and down on the left, and then the same number of particles, quarks, when we add another third quark, which is different. So because we can have two particles in the same state as those are fermions, the total energy when we are adding different particle can be lower.
Yes.
And then what can be when we are mixing with another quarks, maybe? I have no idea.
So the curve values of bag constant, what is this unit? 160, 170? What is this bag?
This is MeV to 1/4. It's related to the pressure from the outside, which which must take place to compensate the. It's difficult for me to explain. I'm also experimental physicist, not in theory. But here we are talking about conditions which have to be satisfied to compensate the forces. So we have a kind of pressure from quarks when they don't want to be in the same energetic state.
That's the Fermi pressure,
Yes,
right?
yes.
This is the Fermi energy, Fermi pressure, yes.
Yes.
Okay, so I should read this paper.
But I will not be able to explain exactly. I never worked on the models.
Yeah, so no problem.
But maybe in future.
And maybe, if I may, a second question about your piezoelectric sensor there. The range of masses of 10 to minus 8 grams, or 1 nanogram, between 1 and 10 nanograms. So this is, I have not understood this mass. Is the mass of the strange quark matter that you want to detect there, or what do you?
Yeah. So this is the mass of potentially particle, which could transfer energy when it's heating with speed around 200 kilometers per second okay. or higher. So then, if it will be strange quark matter or any other particle which can transfer the energy, we don't know. But by now, in the test, we estimated that we can measure up to 10 to minus 6-7 grams, not 9. But we are working in laboratory with noises, and it will be a bit better.
Thank you.
We are using commercial detectors, nothing, not space qualified, not yet.
Thank you very much, Zbigniew. Let's thank our speaker again and all the speakers of this session. And I think we still have, 10 minutes to grab coffee.